Hello, I'm John Fiorenza, a design engineer with Linear Technology. Today, I will be talking about making wide common mode voltage range current measurements with the LT6375. The LT6375 is a difference amplifier that provides an extremely accurate differential gain of 1 for measuring signals with common mode voltages of plus 270 volts, minus 270 volts, and everywhere in between. It makes a differential measurement and translates it from a high common mode voltage down to a low voltage, so it can be digitized by an ADC. The voltage on the ref pin allows you to line up the output signal range with the input range of the ADC. The LT6375 is exceptionally well suited for current sensing applications. It can be used to make a very accurate measurement of a current across a small sense resistor and directly drive an ADC. It works in a wide variety of current sensing applications, including high-side current sensing, low-side current sensing, negative high-side current sensing, and bidirectional current sensing. We will focus on high-side current sensing in this presentation, but all of the advantages we mention apply to all current sensing applications. Alternative industry standard difference amplifiers lack the accuracy of the LT6375 and are much less flexible in their usage. Prior industry standard difference amplifiers operated with a large common mode input voltage by dividing down the common mode voltage by a factor of about 20. Although this division approach enables measurement of very high common mode voltages, it amplifies the noise and offset of the internal op-amp. The LT6375, on the other hand, has a flexible resistor divider ratio at its input. It has pin-strappable reference resistors. Tying the reference pins to ground or to a low impedance reference voltage allows you to set the resistor divider ratio. Here we see the LT6375 configured with a resistor divider ratio of 20, similar to the industry standard difference amplifier. With the LT6375, you can make a trade-off between input voltage range and output noise and output offset. Tying more reference resistors to ground creates a higher resistor divider ratio, which allows for a higher input range, but reduces accuracy of the amplifier. Using a lower resistor divider ratio lowers the input range, but increases accuracy. 7 ratios between 7 and 25 are available. You should choose the lowest resistor divider ratio that meets your input range requirements. For certain choices of input voltage and power supply voltage, the voltage division ratio of 20 is appropriate. If such a wide input common mode voltage range is not required, the voltage division ratio of the LT6375 can be reduced. If the maximum required input range is 90 volts, we can use a resistor divider ratio of 7 and consequently improve the noise and offset performance of the amplifier. Additionally, the LT6375 has a wider supply voltage range than the industry standard difference amplifier. This allows you to use a low resistor divider ratio for a high input common mode voltage measurement. Here we can see that we can use plus and minus 25 volt supplies and a resistor divider ratio of 12 with the LT6375, while the industry standard amplifier is on its maximum plus and minus 15 volt supplies and its fixed resistor divider ratio of 21. This allows the LT6375 to have superior performance. A higher resistor divider ratio is also supported by the LT6375. This allows you to reduce power by using a lower supply voltage while still accurately measuring a high input common mode voltage. Using a resistor divider ratio of 25 in this application allows the LT6375 to handle a higher input common mode voltage than the alternative amplifiers. The internal op-amp in the LT6375 has a feature unmatched by the competition. The op-amp will continue to operate if its inputs are above its supply voltage. We call this over-the-top operation. This feature allows the difference amplifier to continue to operate at a reduced performance level when the inputs are far higher than the supply voltage. In fact, the inputs to the internal op-amp can go to 76 volts above V-, independent of the V+ supply voltage. This feature is useful in applications where you need to handle very high input voltages and you cannot use a high supply voltage, but accuracy is not the primary consideration, or in applications where you would expect to temporarily see very high input voltages. As you can see from the previous examples, the LT6375 allows you to tailor your circuit to your current sensing application to achieve higher system performance. The LT6375 is available in much smaller packages than the prior difference amplifiers. It is packaged in space-saving leaded MS16 and leadless DF14 packages. The LT6375 has two additional features unmatched by the competition. It has a shutdown pin that can be used to achieve significant power savings in low duty cycle applications, as well as thermal protection circuitry, which increases robustness by preventing the amplifier from overheating. In addition to current sensing, the LT6375 is well suited for a variety of applications that can benefit from a high voltage precision difference amplifier. This is an example of one such application. Here we see the LT6375 arranged in a different fashion in order to produce a differential gain of 1/6 rather than a gain of 1. This allows us to measure the full minus 48 volt battery voltage and produce an output voltage that can be processed by lower voltage circuits. The LT6375 datasheet includes a variety of applications that can demonstrate the general purpose characteristics of the amplifier. Please visit us at linear.com for more information. Thank you.